Hello students. So today we are going to solve the NCERT Exemplar questions of our chapter 7, that is alcohol, phenols and ethers. And we are going to solve question number 3, 4, 18, 21, 23, 26, 28 and 40. This is the disclaimer. Now, what is the objective of today's lecture? So, after attending this lecture, you will be able to solve the NCERT Exemplar questions of alcohol, phenols and ethers. Okay, so let's start with today's lecture. So first we are going to solve NCERT Exemplar question number 3. So let's see what this question is saying. So it is asking that what is the correct order of reactivity of alcohols in the following reaction. So a reaction is given to you, okay, and you have to tell that what is the correct order of reactivity. 4 options are given. You have to choose one of the correct answer. So I am giving you some time to think and then we will discuss. Okay, if we see the solution part, then the right answer for this question is option number C, which is tertiary. First is of tertiary, then is of secondary, and then is of primary. Now let's see the solution, that how this option is correct. So see, this reaction is given to you, okay, what is happening in this reaction? So this is an alcohol. When alcohol reacts with your hydrochloric acid, which is HCl, in the presence of zinc chloride, so it forms an alkyl halide and water. Okay, so this is what is happening in this reaction. Now this given reaction, it is used to distinguish between primary, secondary and tertiary alcohols, which is based on their reaction rates. So this is a very famous test which we called it as Lucas test. Okay, so this is used to distinguish between your primary, secondary and tertiary alcohol. Okay, so this test is famously called as Lucas test, which is named after Howard Lucas, who developed this particular method. Okay, so what happens in this reaction, that when you react your alcohol with hydrochloric acid in presence of ZnCl2, so this reaction proceeds by an intermediate, and that intermediate is a carbocation intermediate. So the key concept over here is the stability of the intermediate. So the stability of your intermediate, it determines the rate of reaction. So higher will be the stability of intermediate, higher will be the reactivity of the reactant molecule. Okay, so the more stable will be your intermediate, the faster the reaction will proceed. So if I talk about the stability of carbocation, then tertiary is the most stable one. Then comes the secondary and last is the primary. So it is saying that tertiary carbocation is the most stable carbocation. Okay. So what is the reason that the tertiary one is the most stable carbocation? It is because of the plus I effect of the alkyl group. If I take tertiary one, in tertiary one, 3 alkyl groups are attached to your carbon atom. If I talk about secondary, then 2 alkyl groups are attached to the carbon atom. And if I talk about primary, then 1 alkyl group is attached to your carbon atom. So in tertiary, there are 3 alkyl groups. Okay, so these alkyl groups, they donate the electron density, which stabilizes the positive charge of your carbocation. Okay, so here there are 3 R. So 3 alkyl groups, they are donating the electron density, and which is stabilizing your positive charge of carbocation. That is why your tertiary carbocation is the most stable carbocation. Okay, if I say about the order of reactivity of alcohols, then it is tertiary, then secondary and then the primary. So the correct option for this question is option number C. Okay, that is tertiary, secondary, and primary. So if I talk about Lucas test, then in Lucas test, your primary alcohol when reacts with HCl in presence of ZnCl2, it gives alkyl halide. So what happens? Your alcohols are soluble in water, but their alkyl halides are not soluble. So if I talk about tertiary one, then tertiary one, it shows the immediate turbidity when it in the Lucas test, whereas the secondary one, it shows turbidity after some time. And if I talk about this primary one, then in Lucas test, this primary one do not show turbidity at all. Okay, because see, the intermediate of this primary one is very less stable, because the carbon to which there is only one R group which is attached to your carbon. So there is only one alkyl group. So the intermediate is not stable. So primary one, they do not show turbidity. Okay, let's move on to the next question. Next question, it is asking that this is an alcohol which is given to you. You have to convert this alcohol into an aldehyde. So it is given, 4 options are given. You have to choose the correct option. I'm giving you some time to think and then we will discuss. Okay, let's see the solution now. So the right option for this solution is option number C. That is treatment with pyridinium chlorochromate. Okay. Now let's see how the solution is correct. So what is given to you in the question? There is an alcohol which is given to you and you have to convert that alcohol into aldehyde. Okay, so here ethanol is given. You have to convert it into an aldehyde, which is acetaldehyde. So for this process, you have to do the oxidation. Okay, so it is an example of oxidation where your ethanol loses hydrogen atom. Okay, so you can think oxidation as gaining oxygen or losing hydrogen. So basically in this reaction, when alcohol will be oxidized to acetaldehyde. So here oxidation is taking place. So conversion of ethanol to acetaldehyde requires oxidation. So if you're doing oxidation, for that, you require oxidizing agents. Okay, so oxidizing agents are substances that can accept electrons from other substances, thereby oxidizing them. So thus, an oxidizing agent is being required. Now let us check all the options one by one. First, we will check the first option, which is catalytic hydrogenation. So this process is actually the opposite of what we need. Instead of oxidizing it, it is reducing the compound. So this is a reduction process. Okay, catalytic hydrogenation is a reduction process. So in reduction, there is gain of hydrogen, or I can say there is loss of oxygen. So what is happening in this catalytic reduction? It adds H2 to double and triple bonds. Okay, so hydrogen molecules are added to double and triple bonds. So this process is used to convert your unsaturated compounds to the saturated ones. Okay, like turning your alkenes to alkanes. So this is a reduction process. So it will convert your aldehyde to alcohol. So this is the reverse of a desired reaction. You have to convert your alcohol to aldehyde, but this is just the reverse. If you see over here, there is acetaldehyde. When you do the catalytic hydrogenation, so this aldehyde is being reduced to alcohol. Okay, so this is a reduction process. We need an oxidation process. So this can't be the correct option. Now we will see the second option. Second option, it is LiAlH4, that is lithium aluminium hydride. If I say about LiAlH4, then this is also a powerful reducing agent. Okay, so LiAlH4 is a strong reducing agent. So it typically adds hydrogen to the compounds, which means it reduces them. So it converts your aldehyde to alcohol. So it will also reduce your aldehyde to alcohol. So this is also a reducing agent. If you look over here, this is your aldehyde. When you use a reducing agent, which is lithium aluminum hydride, LiAlH4, you will see that it will reduce it into ethanol. So this also cannot be a right option. Now we will move to the next option, which is pyridinium chlorochromate. So it is C5H5NHClCrO3. This is your pyridinium chlorochromate. Now, pyridinium chlorochromate is a mild oxidizing agent. Okay, it is crucial because it allows us to control the oxidation process without over oxidizing it. Okay, so because we have to only oxidize alcohols to aldehyde, so we need a mild oxidizing agent. So it specifically oxidizes primary alcohols to aldehydes. So this is the appropriate reagent for this conversion. If you look over here, this is the ethanol. When you use PCC, which is pyridinium chlorochromate, you see this will oxidize this alcohol to aldehyde over here. So this is the appropriate reagent for our conversion. So that is why option number C is correct. Let us see the fourth option, which is KMnO4, okay, potassium permanganate. So KMnO4 is also an oxidizing agent. But why this is not the correct option? Because this is a strong oxidizing agent. So this will oxidize your alcohols directly to carboxylic acid. So it oxidizes primary alcohols directly to carboxylic acid. But we need to stop it at aldehyde. That is why we need a mild oxidizing agent. But KMnO4, if you see over here, this is an alcohol, which is ethanol. When you use KMnO4, it oxidizes it to acid, which is acetic acid. So that is why this option is also incorrect. Therefore, the correct option is C, which is treatment with pyridinium chlorochromate. Okay, this reagent is milder and it allows for the controlled oxidation of primary alcohols to aldehydes without further oxidation to carboxylic acid. Now let us see the next question. Which of the following reaction will yield phenol? So you are given 4 options and you have to tell that which one of them will yield phenol. So 4 reactions are given to you. I'm giving you some time to think and then we will discuss. Okay, let's see the solution now one by one. So correct answer for this question is A, B and C. So all the 3 reactions A, B and C, these reactions will yield your phenol. Now let us see one by one each of this reaction. First reaction is chlorobenzene to phenol. Now look at this particular reaction. Here a chlorobenzene is over here. Chlorobenzene is an initial reactant and finally you are getting a phenol. So this reaction is converting your chlorobenzene to phenol. So what is happening in first step? In first step there is fusion with NaOH at 300 atm. Okay, and this will give you phenoxide ion. Now this process is family known as Dow's process. What happens in this process? That if you see your NaOH, which is a base, so it is Na plus and OH minus ions. Now this OH minus ions will abstract one hydrogen from this position. So when it will abstract one hydrogen from this position, now you know that chlorine is the poor leaving group. So now if you have to leave this chlorine from here, you need a harsh conditions because this is a poor leaving group. So what harsh conditions? You require high temperature and pressure. Then only this reaction will proceed further. Okay, so when your OH hydroxide ion will attack on this hydrogen, so your chlorine will leave and an intermediate will form, which is a benzene and which is highly reactive. Now another OH attacks your benzene at one of the carbon of triple bond. It can attack either on this carbon or this carbon. Okay, it attacks at one of the carbon of triple bond and it forms this, which is sodium phenoxide. And this sodium phenoxide is then further treated with your HCl to give your phenol. So this is what is happening in this reaction. So this is family known as Dow's process. So it occurs under drastic condition, that is 300 atm and 623 Kelvin. Okay, these conditions are necessary to facilitate the nucleophilic substitution. As this aromatic ring is quite stable, this is quite stable, and it is resistant to reaction under milder conditions. So that is why you need these drastic conditions. Then only your substitution will happen. So this is an example of a nucleophilic substitution reaction. So a nucleophile is a chemical species that donates an electron pair. Okay, so it will attack the aromatic ring and it will replace this chlorine atom. So chlorine atom will be substituted by this phenol. So chlorine atom will be replaced over here. So chlorine Cl group is replaced by OH, that is hydroxide. And this substitution is crucial because it transforms your chlorobenzene into the phenol. So this option is correct because from chlorobenzene you are getting phenol over here. But you need to remember this happens under the drastic conditions, which is 300 atm and 623 Kelvin. Now let us look the B option. It is your aniline to phenol. You are converting your aniline to phenol. If you look over here, starting this is your aniline and this is a primary aniline. When you're treating it with NaNO2 in presence of HCl, you are getting a benzene diazonium chloride. So here diazotization is happening. Okay, and this diazotization, this process takes place in low temperature. That is 0 degrees Celsius to 5 degrees Celsius. Okay, so diazotization is happening and your aniline is getting converted to benzene diazonium chloride. And when you treat it with warm H2O, you get your phenol over here. So this is, at first, aniline converts to a diazonium salt. So diazonium salts, they are versatile compounds which are used in your organic synthesis reactions. So this reaction occurs in the presence of NaNO2 and HCl at low temperature. So low temperature, it helps you stabilize the diazonium salt, which prevents its decomposition. So then what happens when you get your benzene diazonium chloride, then this diazonium salt is warmed with H2O to get the phenol. So final product which you are getting is phenol. So this occurs by a nucleophilic substitution pathway. Okay, that your aniline group over here is substituted by OH, that is hydroxide group. So finally you get an phenol. Now let us check the C option. This is benzene to phenol. Now what is happening in this reaction? Initially your reactant is benzene and final product which you are getting is phenol. So what is happening in this reaction, when initially you have a benzene, when this benzene interacts with oleum, it forms a benzene sulfonic acid. Okay, so your oleum over here, if you see, it is H2SO4 and SO3. So when your benzene interacts with oleum, you get a benzene sulfonic acid. So how this transformation is happening? So first step involves your generation of electrophile, which is SO3H+. So in concentrated H2SO4, your sulfur trioxide, which is SO3, it gets protonated. In second step, there is electrophilic substitution. So what is happening in this step? It involves the attack of benzene. It involves the attack on benzene, that is electrophilic substitution. So pi electrons of benzene, they attack SO3H+, forming a resonance stabilized uranium ion. Okay, and the last step involves your deprotonation. That means loss of H+. It restores the aromaticity, giving this benzene sulfonic acid. So this is how from your benzene you get a benzene sulfonic acid, and then this benzene sulfonic acid is then heated with NaOH and it is then further acidified to give a phenol. So this is benzene on treatment with oleum, which is H2SO4 and SO3. It produces this benzene sulfonic acid. So sulfonation is a common method which is used to introduce functional groups into the aromatic compounds. Next, this is known as the sulfonation reaction. So benzene sulfonic acid, it is acid on treating with NaOH, and then it then gets acidified to get the phenol. So this option is also correct, that from benzene you're getting a phenol. Now let us check the fourth option, that why it is incorrect. So if you see fourth option, here you have chlorobenzene. So when chlorobenzene is treated with NaOH, look at the reaction conditions. It is 298 Kelvin and 1 atm. And when you're further acidifying it, you see here there is no reaction. Now why this is no reaction? Because our haloarenes, they are less reactive towards the nucleophilic substitution reaction. So this requires very high temperature, which is 623 Kelvin and pressure of 300 atm. So if this reaction needs to happen, you need to see the reaction conditions. Okay, it requires high temperature and pressure. But if you look over here, the temperature is only 298 Kelvin and pressure is also 1 atm. So that is why there no reaction is happening. This is because the reaction, it needs the significant energy to overcome the stability of the aromatic ring. So because this aromatic ring is quite stable. So chlorobenzene does not undergo hydrolysis on treatment with aqueous NaOH at low temperature, which is 298 Kelvin, and atmospheric pressure, which is 1 atm. So this will show no reactions. So this highlights the need for the extreme conditions to facilitate your reaction. So that is why the correct options are A, B and C, because in D option there is no reaction is happening. Now let us see the next question. Which of the following are benzylic alcohols? So you have given 4 options and you have to tell that which one of them is a benzylic alcohol. So first you need to remember what is benzylic alcohol. Then based on that definition, you will tell that which one is a benzylic alcohol. So I'll give you some time to think and then we will discuss it. Okay students, let's see the solution now. So the correct option for this question is B and C. So your B and C are benzylic alcohols. Now let us check the solution. So first of all, we need to define what are benzylic alcohols. So a benzylic alcohol, it has a OH group that is attached to a sp3 hybridized carbon that is adjacent to an aromatic ring. So what is the main focus here? That the group to which your OH group is attached, it is attached to a sp3 hybridized carbon, and that carbon atom is adjacent to an aromatic ring. So these two things you need to remember, that it should be sp3 hybridized carbon and that carbon should be adjacent to an aromatic ring. So if we look towards compound A and D, then in A and D, the OH group is attached to a sp3 hybridized carbon. So first condition, it is satisfying that our OH group is attached to a sp3 hybridized carbon atom. But that carbon atom is not adjacent to the benzene ring. Okay, if you look at the figures of this question, then you will see that in A1, the OH group is attached, the carbon to which your OH group is attached, this carbon is sp3 hybridized. Okay, so this condition is satisfying. But this carbon is not adjacent to this aromatic ring. If you see, this carbon is adjacent to this CH2 group. But for benzylic alcohols, this carbon should be adjacent to the to this benzene ring. So that is why it is not in benzylic alcohol. Now check option number D. The carbon to which your OH group is attached is a sp3 hybridized carbon. Yes, but that carbon is not adjacent to your benzene ring. That is why they are not the benzylic alcohols. Now let us see why the options B and C are correct over here. So what is happening in compound B and C? The OH group is attached to a sp3 hybridized carbon atom, and that is adjacent to an aromatic ring. So both the conditions are satisfying, that it is a sp3 hybridized carbon as well as it is adjacent to an aromatic ring. So if you see over here, the carbon to which your OH group is attached, this is a sp3 hybridized carbon. And this carbon atom is adjacent to this benzene ring. See, this carbon is attached to this benzene ring. So this is adjacent to this aromatic ring. Similarly, if you see over here, this carbon is a sp3 hybridized carbon. And this carbon is adjacent to this benzene ring over here. That is why your B and C are benzylic alcohol. So you need to remember that benzylic alcohols are those alcohols, the carbon to which your OH group is attached should be a sp3 hybridized carbon, and it should be adjacent to an aromatic ring. So that is why your B and C options are correct. So among them, B is primary and C is, they are secondary benzylic alcohols. So if you see over here, this is a primary benzylic alcohol. Why? Because the carbon to which your OH group is attached is further connected by one carbon atom. So this is a primary benzylic alcohol, and this is a secondary benzylic alcohol. Why? Because the carbon to which your OH group is attached is further connected by two carbon atoms. See, one this carbon atom and one this carbon atom of a benzene ring. That is why this is a secondary benzylic alcohols, but both are sp3 hybridized carbon. So correct options are B and C. So I hope this question is clear. Now let us see the next question. It is asking, what is denatured alcohol? So you need to tell me that what is denatured alcohol. So let us see the solution. So ethanol, which is a drinking alcohol. So the alcohol which is available in the market for drinking, it is ethanol. So ethanol that has been deliberately mixed with toxic or unpleasant substances to make it unfit for human consumption is known as denatured alcohol. So basically your denatured alcohol is essentially a ethanol which is mixed with your toxic or unpleasant substances. And these additives, it makes the alcohols unfit for the human consumption, means further it cannot be consumed. So this process is known as denaturing. Okay, the process of making alcohol unfit for human consumption or undrinkable process is known as denaturing over here, because it alters your properties of alcohols. So the main purpose of denaturing alcohol is to prevent people from drinking industrial alcohol. So one of the primary reasons is to prevent its consumption as a beverage, because it is crucial for public health and safety, as industrial alcohol, it can be harmful if it is ingested. So it makes industrial alcohol cheaper for manufacturing and commercial use. So when you denature it, it will make your industrial alcohol cheaper. So it reduces the cost of industrial alcohol for manufacturing and commercial purposes. So by denaturing it, manufacturers can avoid the taxes and regulations which is associated with your beverage alcohol. Now, how you make it unfit for human drinking? So, common substances that are added to denature the alcohols. You add some substances which denature these alcohols. So, what are those substances? It is methanol. So, methanol is often used as an additive. So, methanol, is highly toxic. Even the minute quantity of methanol can cause a death of a person. So methanol is highly toxic and it can cause serious health issues if it is consumed. So you can add, if you have to make it unfit or you have to denature the alcohol, you can add the methanol. Or you can add the copper sulfate, which is CuSO4. So this is another additive. So it gives an alcohol a distinctive color and taste. Further, it is deterring it for the consumption. Next is the pyridine. So pyridine is also used in denaturing process. The pyridine, it has a very unpleasant odor and it makes the alcohols less appealing. Next is acetone. So acetone is a solvent with a very strong smell. Okay, and if you must have used the nail polish remover, then in nail polish remover it contains the acetone. So if you smell it, it has a very strong smell. Okay, and it further you can use this for denaturing process, which makes it unfit for the human consumption. So if you're adding these substances, you can denature the alcohol. Now let us see the next question. Out of 2-chloroethanol and ethanol, which is more acidic and why? So you have been given 2-chloroethanol and ethanol, and it is asked that which one is more acidic and why. So I give you some time to think and then we will discuss. Now let us see the correct option. So if I asked about that, how, on what basis you tell which is more acidic? So a compound which can easily donate its H plus is more acidic. So we have to check out of 2-chloroethanol and ethanol which can easily donate its H plus. Okay, which will easily donate its proton will be more acidic. First, let us see for 2-chloroethanol. Then in 2-chloroethanol, you see you have a chlorine atom. So chlorine atom in 2-chloroethanol has a inductive effect, has a minus I effect. That is, this chlorine atom has minus I effect. That means it will pull the electron density away from the carbon chain. So being it has minus I effect, so it will withdraw the electron density from the carbon chain, and this withdrawal, it decreases the electron density around the oxygen atom, okay, which will make it easy to release a hydrogen ion, that is H plus ion. So it will decrease the electron density on the oxygen atom, and it will make the OH bond more polar. If it will make the OH bond more polar, then it can easily donate its H plus ions. So it will facilitate the release of H plus. Now if you look at this figure, you see this is 2-chloroethanol, that on second carbon this chlorine group is attached. Now this chlorine has a minus I effect. So this chlorine atom will withdraw the electron density from this carbon, which will further withdraw the electron density from this carbon, and this carbon will withdraw the electron density from this oxygen. So that means the electron density on this oxygen is decreasing. Now if the electron density on this oxygen is decreasing, what it will do? It will take the shared pair of electrons from this hydrogen, because now this oxygen is hungry, because this chlorine is taking away its electron density. So this will say to it, this hydrogen, that I need to take the shared pair of electron towards me. So this will make your oxygen hydrogen bond more polar. So this bond will become more polar, or I can say this OH bond will become weak. So this H plus can easily leave from here. So it will facilitate the release of H plus. So that is why it can easily release its H plus ions. So this will be more acidic over here because of the minus I effect of your chlorine atom. So it will pull the electron density away from the carbon chain, which will affect your OH bond. Now if we see about ethanol, then what happens in ethanol? If you see the case of ethanol, then ethanol, this is a simple alcohol which has a CH3CH2 group, and this group has a positive inductive effect. That is, this alkyl group has a plus I effect. That means it will push the electron density towards the oxygen atom. So it will make your oxygen hydrogen bond less polar compared to 2-chloroethanol. So it will increase your OH bond strength. So your release of H plus becomes difficult in this case. If you look over here, then this CH3CH2 is an alkyl group, that it will push the electron density towards this oxygen of OH bond. Now the stomach of this oxygen is fulfilled because it is getting the electron density, because these are electron donating in nature. So it will push the electron density towards this oxygen. Now because the stomach of this oxygen is full, it will not take the shared pair of electrons from this hydrogen. Okay, so if it will not take the shared pair of electrons from this hydrogen, so this bond will become less polar. That means this OH bond strength will increase. So it will be difficult to release this H plus over here. So that is why if it is difficult to release H plus, this will be less acidic as compared to 2-chloroethanol. So 2-chloroethanol will be more acidic than ethanol because this chlorine atom has minus I effect. Okay, so this will make the OH bond more polar in 2-chloroethanol and H plus will release easily. So therefore 2-chloroethanol shows greater acidic character than ethanol because of the presence of an electron withdrawing chlorine atom. Now let us see the next question. You have to write the structures of isomers of alcohols with the molecular formula C4H10O. Which of these exhibits optical activity? So you have to give the structures of the isomers of the formula C4H10O and which of them exhibit the optical activity. So let us see the solution. So we will talk about in terms of chirality and optical activity. So chirality is a property of a molecule that makes it non-superimposable on its mirror image. Okay, much like your left and right hands are mirror images, but they are not identical. And this is crucial because chiral molecules, they have the property that they can rotate the plane polarized light, and that property is known as optical activity. So optical activity is rotation of the plane polarized light, which is shown by the chiral molecules. So a molecule is chiral if it contains a carbon atom that is bonded to 4 different substituents. That is, the 4 different substituents to which a carbon atom is bonded, that substituent should be different. So presence of 4 distinct groups around a carbon atom is the key to its chirality. Now such a carbon is called an asymmetric carbon or a chiral carbon. So either it is called a chiral carbon or you can call it as a asymmetric carbon. Now optical activity, it is the ability of a substance to rotate the plane polarized light. So optical substances, it can rotate the plane polarized light. This is the optical activity. And chiral molecules are optically active. So if a molecule has 4 different substituents, that is a chiral molecule, and that molecule is optically active. That means it can rotate the plane polarized light. But achiral molecules, they are optically inactive. That means it cannot rotate the plane polarized light. So this distinction is important in understanding that how molecules interact with light and other chiral substances. Now, the molecular formula which is given to us in the equation is C4H10O. So it has 4 different isomers if you see over here. First is butane 1-ol. If you see 1, 2, 3, 4. There are 4 carbon atoms in this chain. So the root word will be but. And to first position, your OH group is attached. This is butane 1-ol. Next isomer is butane 2-ol, because the carbon to which your OH group is attached is second carbon. 1, 2, 3, 4. So this is butane 2-ol. If you look over here, this is 2-methyl propane 2-ol. If you see over here, then on second position, there is methyl group attached and 1 OH group attached. So the numbering is 1, 2, 3. So this is 2-methyl propane 2-ol. Next isomer, if you see over here, this is 2-methyl propane 1-ol over here. If you do the numbering, then 1, 2, 3. On second position, a methyl group is attached, and on first position, your OH group is attached. So these are the 4 isomers which is possible of the molecular formula C4H10O. Okay, now if we look over all these four compounds, butane 2 all has a chiral carbon. How, if we look at this, then it has four different groups. One is this OH group, one is this CH3 group, one is this CH2 group, and one is this hydrogen. So all the four substituents which are attached to this carbon are different. So this is a chiral carbon. If you look over here in butane all, then there is no chiral carbon which you will see. And if you see in this 2-methyl propane 2 all, then you will see that this carbon is connected by same 3 methyl groups. So this is also not a chiral carbon. And in this also, if you see over here, this carbon, it is attached to 2 methyl groups. So this cannot also be a chiral carbon. So only butane 2 all is a chiral carbon because it has a carbon atom that is attached to 4 different groups. So therefore, this butane 2 all is only optically active isomer because only the chiral molecules are optically active, that they can rotate the plane polarized light. So since this is chiral carbon, so this is only optically active among all the isomers which is given to you. Okay. So thank you, students. This was it for today's lecture. I hope you have a good day.